Hi there, folks. Today we're looking at special right triangles. There's two of them we're going to look at. Those are 45-45-90 triangles and 30-60-90 triangles. And really, they're just triangles that come up and they get used quite a bit. And we have some shortcuts for bouncing back and forth between the different side lengths and whatnot. So that's what we're essentially going to look at today is just these special right triangles and the relationship of the sides of those right triangles, okay? So if I were to look at the first one, it just asked me for all of these just to find the missing measurements. And here's the thing, we can find all the missing measurements of this thing without realizing this is a special right triangle. So if I look at this thing, right away I can find the missing angle because all the angles inside of a triangle have to add up to 180 degrees. And so as I look at this is a 90 degree, a 45 degree. This one has to be a 45 degree angle as well. Okay, that's what I need in order for these to add up to a 180 degrees, all right? And then from there, when you think about this, because the base angles are the same, if these angles are the same, the relationship within a triangle is if I have two angles the same, then the sides opposite those angles also have to be the same. So this side has to be a 1 just based on the fact that essentially I have an isosceles triangle. And I know it's isosceles because the base angles essentially are the same if I were to kind of rotate this thing. All right, but again, that's the relationship the angles and the sides have within one triangle. If the angles are congruent, then the opposite sides are congruent, okay? And then the missing side that's left, well, this is a right triangle, and that's the hypotenuse. I just have to do my Pythagorean theorem. And so if I do the Pythagorean theorem, 1 squared plus 1 squared equals, and again, we'll call this C, equals C squared. So that's 1 plus 1 equals C squared. So C squared equals a 2. I take the square root of each side. So I get C equals the square root of 2, and that's it. And I'm going to leave it in radical form because we want an exact value here for these guys. So that's the square root of 2. There it is. If I look at the next one, again, I got a lot of missing pieces here. But one of the things that we can look at, right now it looks like we have two right triangles. Well, instead, let's just look at it as one single triangle. And if you kind of look at this as one single triangle, if I were to kind of ignore that altitude that's drawn there, well, this would be an equilateral triangle. This would have to be 60 degrees as well, this whole angle up top here, okay? So now if all three of those angles are 60 degrees, it means all the sides are congruent. This is an equilateral triangle, which means also that when we draw that altitude, and this is true for, this is a corollary that we have for equilateral triangles, but if I have an isosceles triangle and I draw an altitude, it's a perpendicular bisector. Well, if I have an equilateral triangle and I draw an altitude, it's also a perpendicular bisector then. So that means this is 1 right here, which means this entire side is 2, which means this side is 2, and this side is also 2 because I've already established that this thing's an equilateral triangle. So we can bounce around here just using some of the previous knowledge we have for triangles. And so now kind of zoom in back out on this thing. Let me erase all the stuff that was unnecessary. If I look at each of these triangles individually now, instead of looking at one big triangle, well, I know that this has got to be a 90-degree angle because those are a linear pair. I now look at each triangle and say, hey, you know what? These have to add up to 180 inside each triangle, so this has to be 30 degrees. This one also has to be 30 degrees. And now I have every piece of this thing. And so, again, we look at the triangle as a whole as an equilateral triangle, and then we look at those two triangles separately to kind of figure out all the different pieces here. All right. The only thing that's missing right now is the altitude, which once again, that's going to be my Pythagorean theorem. And if I look at just one of these individual triangles, I'll call that B. So I'm just going to use my Pythagorean theorem, a squared plus b squared equals c squared. Let's see, that's going to be a 1 squared plus b squared equals 2 squared. And so now that's a 1. If I guess I'll show a little bit of work here. And now I subtract that 1 from each side and then take the square root. So I got b equals the square root of 3, and there it is. That's my missing piece. And again, I'm just going to leave it in terms of the square root. So right here, that's the square root of 3. And now I have all the missing pieces. Okay, don't forget about that altitude. If I look at the next one, same kind of thing, I can kind of take the same approach here. I know that this thing's an isosceles triangle, or I just know that the relationship in the triangles, if I have two congruent angles, the sides opposite those angles are also congruent, so this is 1/2. And then I could find the missing side using the Pythagorean theorem. So it's 1/2 squared plus 1/2 squared equals c squared. Again, I'm just referring to that missing side of c because it's the hypotenuse. So that's 1/4 plus 1/4 equals c squared. That gives me a 1/2 equals c squared. And now I take the square root of each side. And so I get c equals the square root of 1/2, which is actually the square root of 1, which is 1, over the square root of 2. And then I have to rationalize that denominator, multiply by root 2 over root 2. That's root 2 over 2. Okay, so that's that missing side. So right here, root 2 over 2. And now if I look at the next one, once again, this is a similar to the triangle I had above it. But before, I had a second one of these triangles drawn, and that's the key. Without knowing the rules for the special triangles, I would have to extend this. Let me draw a triangle here that's equivalent to that first one. 60 degrees, 30 degrees, 90 degrees, and they share this side. Okay, so angle, side, angle. I've just drawn a congruent triangle to this thing. Well, what I've done now is I've essentially made a big triangle that's got 360-degree angles, which means this thing is an equilateral triangle. It also means that that bottom piece, this guy right here, that's congruent to itself, that has to be an altitude when I kind of turn this thing sideways, and it's also a perpendicular bisector. So once again, I'm in the same situation. This has to be a 3. All the sides here have to do the same, so that's 6. This is 6. Okay, and now I can find that missing side simply by doing the Pythagorean theorem. So I don't need this second triangle anymore now that I've established that 6. Now I can do the Pythagorean theorem. Once again, that's going to be a squared plus b squared equals c squared. Again, make sure you have the hypotenuse in the right place here. I subtract the 9 from each side, and I take the square root. Sorry, that's a 27. And now let's simplify this thing. So b equals 27 is 9 times 3. The square root of 9 is a 3, and there's a 3 left over. Okay, so I get b equals 3 root 3. That's this missing side right down here. Okay, and so as I look at this, hopefully you kind of see a relationship here. Like when you look at this first one, sorry, my screen went a little wonky there. When I look at this first one, I see a 1 here and a square root of 2 here. And when I look at the one underneath it, I see a 1/2 here and a square root times 1/2 essentially over here. When I look at this guy, I see a 1 here and a 2 here. When I look at this guy, I see a 3 here and a 6 here. Okay, so hopefully we're starting to establish a relationship. Here I see a 1 and a root 3. Here I see a 3 and a 3 root 3. Okay, and so kind of looking at this, that idea that, you know, there's clearly a relationship here. There's some kind of pattern when I look at a 45-45-90 triangle versus a 30-60-90 triangle. There's a relationship between the two 45-45-90s, and there's a relationship between the 30-60-90s. And that's kind of what we're after here. And when you look at these first two, these are kind of like the base version of this thing. All right, and so here's what it looks like. 45-45-90 triangle will always be in the ratio 1 to 1 to 2 to root 2. Okay, and you know, when you think about that, that was the very first one that we did, and the second one we did is in that same relationship, except this was a 1/2, this was a 1/2, so now this is a divided by 2. Essentially, we're saying that it's proportional to that first one and proportional to this guy. And so that's the idea here, is that all 45-45-90 triangles are proportional. So if the one of them has this relationship, has this ratio of 1 root 2, they all have that ratio of 1 root 2. Okay? Yeah, we might change each of those values by multiplying each of them by the same thing. Like if I made this a 2 over here, and I made this guy a 2, then this guy would be a 2 root 2, all right? If I made this guy a 3 over here, but again, we're holding the proportionality. If that's a 3 and this is a 3, then this is a 3 root 2. Okay, so it still has that same proportionality. It still has that same ratio between the legs and the hypotenuse, all right, as the very first one that we explored. Likewise, the 30, 60, 90 triangle has a ratio of 1 root 3, 2. And I always try to think of this as like a 1, 2, 3 triangle. Just kind of helps me remember those. I just have to make sure they're in the right place. 1 is the short side, 2 is the hypotenuse, and then it's root 3 for that larger of the two legs, okay? But again, this was the ratio that we had in the very first 30, 60, 90 triangle that we explored. And then after that, the next one, I think instead of a 1 here, we had a 3. Instead of a 2 here, we had a 6, which is like 3 times 2. And over here, we had a 3 root 3. And so that's the idea here, is that all 30, 60, 90 triangles are going to be proportional, are going to be similar to this base 30, 60, 90 triangle, okay? So if this one has a ratio of 1 to root 3 to 2, then every 30, 60, 90 triangle has a ratio of 1 root 3, 2, okay? And so that's kind of the idea here. All other triangles, all other similar triangles are similar by angle. So again, all 45, 45, 90 triangles are similar to the first one that we did, all right, because of angle. All 30, 60, 90 triangles are similar to the one that I have displayed right here because of angle, which means if I remember this relationship, so if I remember just this original triangle right here, if every 45, 45, 90 triangle is similar to this one, I can just remember these ratios, the 1, 1, root 2, and then set up a proportion to solve for the missing side of any 45, 45, 90 triangle. Same thing with this guy. If I just remember this original triangle right here, this 30, 60, 90 triangle, and I remember that ratio of 1, 2, root 3, then that means any other 30, 60, 90 triangle, I can find a missing side of that by saying, hey, it's similar to this guy, so I can set up a proportion, a similarity proportion in order to solve, okay? And so here's what this is going to look like. Ready? So if I look at something like this guy, again, if we think about the original triangle that I just had drawn moments ago, it looked like this. It was 45, 45, 90, and it was in the ratio 1, 1, root 2. Okay? And so here's the thing, at 45, 45, 90, if it has this ratio, every other 45, 45, 90 triangle is similar to the one that I have circled here, that I have that box around in red, okay? Which means this guy and this guy, well, these are similar triangles. So if I want to find the missing side of this thing, I can easily do that by setting up a proportion with the similar triangle. And so when you look at this, if I say, hey, the original triangle was 1, and the new triangle has a leg of 4. So 1 to 4, comparing those sides, is the same as like this guy down here. I'll call it x. This is going to be 1 to x, so equals 1 to x. And now I can cross multiply and solve, and I get x equals 4. Well, of course it's going to be 4. This is an isosceles triangle, so now I have this missing side. Likewise, for the hypotenuse, I'll call it y this time. It's going to be similar to that original triangle. So if I use this same relationship, let me do it again here. Oh, I erased this guy. But if I compare the sides here, this one here, 1 goes to 4, the same way that root 2 goes to y. And because these are similar triangles, that's what I can do. I can set up a proportion here and say root 2 compares to y. And now I can cross multiply and solve. So I cross multiply, I get y equals, that's going to be 4 root 2. And so now I have this missing side, and that's it. All right. So again, it's that idea that if I understand, if I remember the original special right triangle, the 1, 1, root 2, every other 45, 45, 90 triangle is similar to that. So I can set up proportions, I can set up ratios and solve for this thing. So that was 4 root 2. Okay. This one, same kind of thing. And see, when you look at the one that I just did, I could have technically found the 4 without doing a proportion. I could have found the hypotenuse using the Pythagorean Theorem, but something like this guy, I can only do through special right triangle. And so once again, this triangle should be similar to the one that I have in this box right here, okay? And so once again, let me kind of establish this. I'm just going to call these sides, I'll call this x and this y, all right? But if I were to set up a proportion here, I would just compare the sides. I would say, hey, this 1 right here compares to x. So 1 over x equals, well, this other side, root 2, must compare to the hypotenuse here, which is 3. So root 2 over 3. And so I'm setting up a proportion based on similar triangles, same way I've always done it, okay? 1 compares to x the same way that root 2 compares to 3, and now I can cross multiply. So I cross multiply, that gives me an x times root 2, so I'll write it as x root 2 equals 3. I divide each side by root 2, so I get 3 over root 2. The only thing that I have to do here now is I have to rationalize this denominator. If I rationalize the denominator, multiply by root 2 over root 2, that gives me a 3 root 2 over 2, okay? And so that's my value for x. I could do the same thing to solve for y, but since we know that this thing's isosceles, all right, and we know that this is across from a 45-degree angle and y is also across from a 45-degree angle, we don't need to set up another proportion. We can just say, hey, this side's going to be the same, okay? And so when we look at this thing, again, it's similar to the original triangle, so I just have to set up a proportion and solve, okay? If I look at this guy, same kind of thing. If I think about the original triangle was this. This is kind of the one I want to memorize. It was 1, 2, root 3. And that was 60, 30, and the 90. Okay? And so once again, because of angle, that triangle that I have in purple up there, the 1, 2, root 3 triangle, that has to be similar to the triangle that I'm looking at here that has the 5. Okay? And so if these are similar triangles, I can set up a proportion to solve for the missing side. So once again, I'll call this guy x and I'll call this guy y. But I can easily just look at this and say, okay, 1 compares to the 5, so 1 over 5 equals 2 over x. I just compare each of those sides like I do with any other similar figures. And I can cross multiply, and I get x equals 10. There it is. So now I have that missing side. And now if I want to solve for y, once again, I set up a proportion here. I would say that, hey, 1 goes to 5 the same way that root 3 goes to y. Okay, so I set up my proportion, I cross multiply, and I solve. So I get y equals 5 root 3. And that's it. And so right away, because this thing is similar to the original, if I know the original triangle, if I remember that pattern of 1, 2, root 3, all right, then I can easily come up with the missing side of any 30, 60, 90 triangle because it's proportional. It's similar to that original triangle. Next one, same kind of thing. If I do the same thing here, once again, the side that I have is the side that's matched up with the root 3, so I set up a proportion. Here, let me label these sides. I'll call this one x, and I'll call this one y. And so as I look at this thing, I would say, okay, root 3 compares to the 10 the same way that 1 compares to the x. Again, I just look at the corresponding sides. I set up my ratios, my proportion, and now I cross multiply and solve. So let's see, that's going to be an x root 3 equals 10. I have to divide each side by the root 3. And now once again, rationalize the denominator. Multiply by root 3 over root 3. 10 times root 3 is a 10 root 3. Root 3 times root 3 just gives me a 3. Okay, so that's the missing side over here. That was x. And now to find y, I can once again set up a proportion. I can say, hey, let's start with that same proportion of root 3 over 10 equals, well, over here, that's going to be 2 over y, okay? And so if I have that proportion set up, I just cross multiply. Once again, that's going to be a y root 3 equals a 20. I divide each side by root 3, so I get y equals 20 over root 3. Once again, rationalize the denominator. That's going to be a 20 root 3 over 3. So there's that missing side. Okay? But again, if you know the original triangle, every other 30, 60, 90 triangle is similar to that one. You can always set up a proportion and solve. Okay? Now from here, I don't want to have to do that every time. Okay? So hopefully you're looking at this going, I think I can shorten this up. There is a shortcut that you can take here. You don't have to do proportions at all. Just look at the relationship between each triangle. Like here, we already have one of these pieces established. Like in 45, 45, 90, we always know that these sides are the same, okay? That goes back to our original relationships within triangles, okay? But then from this side to this side, it's just a root 2 tacked on there, which means you're multiplying by root 2 to get here, okay? But then think about it. If I wanted to go backwards, if I wanted to go from the hypotenuse back to this leg, I wouldn't multiply by root 2. I'd actually divide by root 2. And you can use that as a shortcut. Look at how it works on this one. Right here, to get from this side to this side, just divide by root 2. Okay? And 3 divided by root 2 is what we got when we solved this thing. And then when we rationalized the denominator, I got the 3 root 2 over 2. Okay? If I wanted to go from this side to this side, I would just multiply by root 2. And that would give me a 3 when it was all simplified. Okay? When you look at these guys, again, when you look at this guy from here to here, it's just times 2. So if I want to go backwards, it would just be divided by 2, okay, to get from this guy to this guy. Okay, that's the kind of shortcuts we want to look for. And then here's the other relationship right here. To get from here to here, it's times root 3. To go backwards, guess what? It's going to be divided by root 3, okay? And so when you look at that from the perspective of this triangle, it's really easy to get from that short side to the hypotenuse, just times 2. To get from the short side to the long side, it's just times root 3. And then when we look at this one, here it is, look. To get from here to here, watch this. Divide by root 3. And when I do 10 divided by root 3 and rationalize the denominator, I get this guy. I get this thing that's right here. And then to get from here to here, it's just times 2. And look at that. All I do is 10 times 2 is 20. Okay? So again, that relationship and understanding how to get back and forth between these things, that can be a huge shortcut. Okay? So when we look at these guys, can we find the missing length of the sides without setting up a proportion? Well, if I look at this guy right here, these sides have to be the same, so it has to be 5. To get from here to here, I just multiply by root 2. So that's 5 root 2. That's it. If I look at the next one, same kind of thing. To get from the hypotenuse back to the leg, to get from the leg to hypotenuse was times root 2. So to get back to the leg, I just divide by root 2. So 6 divided by root 2. Again, rationalize the denominator. That's going to be 6 root 2 over 2, which is 3 root 2. So that's what this side has to be, 3 root 2. And this side has to be the same, 3 root 2. Sorry, I should have given myself a little bit more space there. Okay? Okay, but again, I was just dividing by root 2 and rationalizing the denominator. Sorry, I wanted to put my work back up here. Okay? If I look at the next one, same kind of thing. That short side, that's like the key. That's the gatekeeper. From the short side to get to the hypotenuse is just times 2, 14. To get to the longer side is just times root 3, so 7 root 3. Okay? The tricky thing is when you don't have the shorter side, you have to work backwards to it. To get from here to here, so again, from the short side to the long side was times root 3, so to go backwards, well, it's divided by root 3. Okay? This is the shortcut that we can take, and then rationalize the denominator. Okay? So now this side is an 8 root 3 over 3. And now to get from the short side to the long side, we're back to that, hey, it's just times 2. So that's going to be 16 root 3 over 3. Okay? That's where what we really want to do with these. We want to use those shortcuts of, hey, 45, 45, 90. I have to get from the leg to the hypotenuse times root 2. To go backwards, divide by root 2. Okay? In the 30, 60, 90 triangle, from the short side to the long side, it's times root 3. From the short side to the hypotenuse, it's times 2. And if I want to work backwards, hypotenuse to short side, divide by 2. Long side to short side, divide by root 3. Okay?